Our next topic is a concept called aliasing. It's a somewhat hidden situation in programming, so let's begin with another practice programming task about merging two lists. So this task says, write a function that accepts two lists of numbers as argument and merges the elements into a new list by repeatedly comparing the first elements from each list and storing both in ascending order. So looking at the example, we have two lists colorized here for convenience. The first one is 284 and the second 619, etc. The first elements from each list are 2 and 6, and then if we look at how they're returned, it's 2 and 6 in ascending order. The next two elements would then be 8 and 1, and if we look at what it returns, it's 1 and then 8 in ascending order. And we continue this process comparing the first elements from our list all the way down, so the next 2, 4, and then 9 show up in ascending order as well. And then once we've run out of items to compare, so the 5, 7, and 3 from the second list there, those just get added to the end of our result. All right, so that's a pretty interesting problem. Let's see if we can write some code that solves this task. Returning to VS Code, let's start a new function. We'll call this one def merge lists. That takes in two lists. We'll call them list1 and list2. So given two lists, we want to look at the front of both of those lists, taking all of the elements one pair at a time, comparing them, and then putting the result into some new list. So in terms of design, we're going to have to start with an empty result list. Once we've initialized our result variable, we're going to loop through, repeatedly taking one pair of elements at a time and comparing them. But how long should that loop last, noting that the two lists may not be of the same size? The comparisons only need to occur so long as there are items in both lists. Right? So if we have one list that has one element and one list that has 100 elements, we're only going to do one comparison. So we might say we loop until the end of the first list. But the issue is that it might not be the first list that's the shorter one. The second list could be the shorter one instead. So what we'll do is we'll make sure that the first list is the shorter one. And if it's longer, then we'll switch them. So we'll say make sure list1 is the shorter list. And then if they're the same, we can just ignore that. But if there is a shorter one, we'll make sure it's list1. Once we've done that, we want to repeat this process until we've considered all the possible pairs. And since list1 is a shorter list, we want to repeat this process until we've paired off each element in list1 with something in list2. Right, if there's more items left over in list2, we can deal with those later, but let's go through all of the items in list1, which is the shorter or equal sized list. So we'll say loop until list1 is done. Now in this loop, we're going to do the process that was asked in the programming task, so we'll take the first element of both lists, and then we'll compare them. So compare to see which is smaller. We'll have to know which order those two items go into, and then we want to put both of those items into the result list, making sure that the smaller of the two items comes first. So we'll say put them in the result list with the smallest first. Once we've completed this loop, comparing each possible pair of items in our lists, what we're left with at the end of that is any leftover items. So if one of those lists is larger, then all the items that can't be paired off should just be included at the end of the result. So we'll say append all of list 2's remaining items, and then we're done, so return the result. All right, we've designed this out in some pseudocode comments here, so now let's walk through each comment and turn it into code. So we want to start with an empty result list, so we'll say result equals empty list. And now we need to make sure that list1 is the shorter list. Another way of saying that is if list2 is shorter than list1, we should switch which list is which. We'll just switch the labels or which variables are pointing at them. So I can say if the length of list2 is less than the length of list1, then list2 is the shorter list, so that's now our limiting list. Then let's swap it. Let's make it so all the items in list2 are in list1, and all the items in list1 are in list2. And the simplest way to do this, we might think, is just to say list2 equals list1, and list1 equals list2. We saw this in the chapter on variables, that if we do this, after line 75 here, after our first action, we'll have taken the value in list 1, which is the whole list, and stored it in list 2, which means the thing that was previously stored in list 2 is no longer referenced. So when we say take everything in list 2 and store it in list 1, we're just copying the thing that we just previously copied the line before. To solve this, we need some third variable to temporarily store the value of one of these variables so that we can make this swap. So let's get rid of these two, and we'll say instead temp equals list2. Doesn't matter which one we pick here. But then the next line is important. Since we've taken the value from list2 and duplicated it into temp, that means the variable list2 is now available for some new storage. So the next line takes the value on the right-hand side and puts it on the left. So list2 equals, and now we can take the original swap we wanted to do, list1. And now the value of list2 originally is stored in temp, and we need to put that into list1. So we'll say list1, again taking the right-hand side and putting it on the left, equals temp. If this didn't make sense, I encourage you to draw it out. Draw two boxes on a piece of paper with some numbers in them, and try swapping them without using some third variable. And then attempt to do it with a third variable and see the order of operations that it's required. And you should see something to the effect of what we've written here. So at line 78, once we've gotten past this if statement, we can guarantee either the lists are the same or list 1 is shorter. Now the way this loop works is going to take elements out of both of these lists, compare to see which is smaller, and then put those elements into some new list. In order to facilitate this, what we're actually going to do is remove the elements, or pop them out of our list, so our lists are going to get smaller and smaller. So after we've done the first comparison, the next comparison will still be at the front of our list, because we've removed the previous front, so the second items have now moved up. So what this means is, in our loop, we're going to repeat until that list, that smaller list, is completely empty, because we're going to get it smaller and smaller each time through the loop. So we'll say, well, the len of list 1 is greater than 0, so long as there are still elements in our list, then we'll continue to loop. And in that case, we'll take the first element of both of these lists, and we've seen just recently how to do that. We'll call it element1 equals list1 dot pop. And you can either say pop 0 or leave it blank and assume the default is 0. I always like to be more explicit, so I'll say pop 0. And then we do the same for the second list. So we say le2 equals list2 dot pop 0. And now once we have these two elements, we can compare to see which one's smaller and put them into the result list as appropriate. So to compare them, say if le1 is less than le2. Here we're assuming our inputs are going to be numbers. And if element 1 is the smaller, then we'll append it to our result first. So we'll say result.append le1, and then result.append le2. If this is not the case, so if le2 is smaller, then we'll say result.append le2, result.append le1. So if element 1 is smaller, then we'll append it first. If element 2 is smaller, we'll append it first. In either case, we're appending both of these values. If it's equal, it doesn't really matter because they'll be the same thing, but you might think for clarity that the input list 1, if they're equal, should come first, so we'll say less than or equal to here. Although technically it would be invisible to any end user if they're just numbers. Okay, now we put them in the result list with the smallest first. Let's get rid of that comment because it's out of place. And then once we've done that, once we've looped through all the items, so we've compared the first two, we go back up, the list still has items, so we remove the next first pair, we compare them, attach them to the result, go back up and check the first pair again, until this is empty. So once list 1 runs out of values, so if the len does equal 0, which should happen eventually because we're always going to pop something, then if there are items remaining in list 2, then we want to append all of those to our result as well. So I can say for every item in list 2, result.append that item. We didn't cover this specific operation, but another way we could have said this is just said result.extend list 2 outside of a loop. So without any loop, it just says extend, and it does effectively this exact same operation. Note if you do this inside a loop, you're going to be extending every time. The loop is to pull items out of our list, whereas extend just takes the whole list. Notice also I didn't have to put an if statement here. There was no check to see if there's items remaining in the list, because if there aren't items remaining in the list, this for loop will just not do anything, and we go on to the next step either way. And once we've done all this work, we're ready to return, so we'll just say return the result. Let's come down to our main method here. Make sure we're running our code, so we'll say print the result of calling merge lists on, and I'll use the numbers from our original task, which are the list 2, 8, and then 4, and then the list 6, 1, 9, 5, 7, 3. That way we can verify if we get the same output as was expected. Save, run our code, and we get the same output, 2, 6, 1, 8, 4, 9, 5, 7, 3. The numbers aren't important, the idea is that we've merged these lists. Now, the reason I wanted to start this video with this example is because it demonstrates an important issue though. Let's try calling our function in a slightly different way. If instead of just merging two literal lists, I created some variables. So I'll say x equals a list, and I'll use same numbers because I'm not that creative today, 2, 8, 4, and we'll say y equals 6, 1, 9, 5, 7, 3. And then instead of passing in literals, we'll pass in these variables, which contain these values. Save and run our code. Nothing has changed. Now the reason I'm doing it this way differently though is what happens to these variables once they're done merging? If I print out the value of x, or let's label it here, x is, and similarly with y, save and run our code again. Notice the final state of our lists is not the way they started. So they started as 2, 8, 4, 6, 1, 9, but they ended with x being empty and y being empty of all but its final 3 elements. The reason for this is because lists are mutable, as we've seen. What this means is changes that we made to this list are happening to the list itself, not the variable representing the list. So inside our function, when we say list1.pop0, we're reaching into that list and we're changing the value of list1, but because list1 is talking about the same actual list as x, it's actually changing x. Now this goes against what I've told you before about scope, where if we pass a value into a function, we can do whatever we want with that copy of that value, and it doesn't affect outside that function. The issue here is because lists are these object types, they're actually not storing the value of the list. Instead, they're storing what's known as a reference. So I've said before that lists are these things called objects, which I haven't really gotten into a lot of detail about them because they're a complex topic and we'll talk all about them in Comp 1406 and at the end of this course. But the idea behind objects is that they're more complex than primitive values. So we've seen primitive values like integers, floats, and booleans. Those are non-divisible values. And the thing that we're storing when we store those values is the value themselves. Objects are non-primitive values. They can contain multiple values of many different types, and they can change size as your code progresses. So consider this image, for example. If we have some list that has 3 strings in it, for example, and we store that list in a variable with the name x, what's actually happening in memory is the variable itself is storing a pointer to the actual list, which is stored somewhere else. That is to say, the variables for object types point to the data. They don't contain it, which is a subtle difference. So you can think of variables for objects as storing the address of the data. Another way to look at this is because lists can change size, they need to be stored in a place where that's not going to cause a problem. We've seen that variables are stored on the call stack when we create functions, and if those change size, then the size of that call stack is going to change, which ends up causing some issues with reading that call stack and adding and removing from it. So instead, these complex types are stored in a different space in memory known as the heap. So the thing that's stored in the stack when we create a list or object variable is a reference to the spot in the heap where all of that data is maintained. Okay, so we have to store something on the stack so we know that the variable x has a name, but we can't store complex data there. So what we're going to store is a reference there, or an address, to where we're storing the rest of the information. Now we can use lists without necessarily knowing that it's doing all of this, but it most notably has an effect when we make what's called an alias. An alias is when two variables refer to the same information, the exact same object or list in memory. Aliases happen when you assign one reference variable to another. So if I had this list x, and then I said y equals x, that says copy the value in x, which again is the address of the list. So now we have a situation as depicted here where we have two variables that both store the same address and they're referencing the same actual information elsewhere in memory. What that means is changes to one of these variables can affect both of them. since they're both referencing the same information. So for example, I could say x equals 1, 2, 3, and y equals x. Then I can say x at 0 mutates its value. So what's the value of x? Change that first value from a 1 to a 4. And if I look at the value of y, it also got changed. Note this same issue doesn't apply to primitive types. If I said something like a equals 5, and then b equals a, so a and b have the same value. If I then change the value of a to say a equals 6, so a now has a new value, b hasn't changed. And this is because primitive types are immutable. They can't be changed in place. We have to make a new value and store it elsewhere. In Python, if we want to know if two variables are referring to the same thing in memory, that is to say if we've created an alias between two variables, we can use the is operator. And the is operator does what's known as identity comparison. It checks the identity of these two variables against each other, which is to say it looks at the address of the space that it's actually referencing and sees, is the object itself, is the list itself the same list, or do they just look the same? So for example, I could say x equals the list 1, 2, 3, and I could say y equals the list 1, 2, 3. I could ask, does x equal y? So two equal signs, comparison. Are these the same value? And that's true, because x and y both look the same. But I could ask, is x the same as y? So x is y? And that's false, because even though they look the same, they're pointing at two separate lists that just happen to be holding identical values. So you can think that's two different places in memory we've stored the numbers 1, 2, and 3. And x is pointing at one of them, and y is pointing at the other. So if we ask, are they equal? Sure. For all intents and purposes, if I ask x at 0, it's going to equal y at 0. If I ask x at 1, it's going to equal y at 1. But if we ask, are they the same thing? No, those are pointing to two different places in memory, so is returns false. But if we made an alias and I said z equals x, so now z has the value 1, 2, 3 as well, I can ask, are x and z equal? And that's true. I can ask, are x and z the same? And that's also true, because we've created this alias. So now we've still only got two lists stored in memory. We've only stored the values 1, 2, 3 twice, but now we have three variables pointing at them. So y is pointing to one copy, and the variables x and z are pointing to this other copy. So this notion of aliasing shows up when we specifically assign one reference variable into another. So when I said z equals x here, for example, that takes the address in x and copies it into z. But a similar aliasing occurs when we use parameters. If I pass a reference into a function, that reference, when used inside that function, is still referring elsewhere in memory, the actual list itself. So we've made a copy of the address, but not a copy of the contents themselves. So as an example of this, consider the following code. So I've defined three functions, foo, bar, and practice, and then I've called practice, so that's kind of our main function here. Inside practice, it creates a variable called x, and then prints it out. We'll modify this code to use the other functions in a moment, but if I were to run this, python aliases.py, you shouldn't have to, but pause and figure out what do you think the output of this function would be. And when we run our code, we can see hopefully you were correct. This just creates a list, the values 1, 2, 3, 4, and then prints that list. Next, what would happen if I were to call foo on that list and then print it again? So what would be the output of this code? So we created a list, we've passed it into this function foo, where the variable x gets the name L. So whatever x was pointing to, now L is pointing to. Right, another way of thinking this is that the value in x, which again is an address, a reference to the actual list, is the thing that gets copied. So we are making a new variable, it's called L, it's got a new spot in memory, separate from the variable x, but it contains the same value. And that value is a reference to the actual list somewhere else in memory. And it's the same reference, so it's the same list. So when we say L at 0 equals 10, that says go to the actual list at index 0 and set the value to 10. So if we come back out into our main function here and we print the value of x, what do you expect the result will be? Save and run our code, and notice the value of x has also been changed. Again, because x in practice is pointing to the same thing as L in foo here, when we mutate this list, we're mutating the same list that this one is looking at. Okay, now what happens when we call the next function? We say bar of x, and then print x again. What do you expect will be the output of this? So similar sort of thing, we're creating an alias where we're taking the value of x, which again is an address pointing to a list, and we're taking that address and storing it in L. So at the first line of bar, that is, say in the header line of bar, when we first create that parameter, it has the value of our argument, which points to the same list object. But then the very next line says, take that variable, the L variable, which again has a separate space in memory than the X variable, just happens to have the same address inside, and instead of storing the address of X, here's a new list to store. So again, this creates a spot in memory for this new list, which has its own address, and stores that address in our variable L. Notice that's replacing the address that was previously stored in that variable. It's not mutating the thing at the end of the list, it's changing the value of the variable itself. And now there are two lists stored in memory, one with the values 10, 2, 3, 4, and one with the values 10, 20, 30, 40. The very next line is the end of the bar function, so this list disappears. We print x, but because x didn't change, we should have the same x as we had before. And we get the same value. So it's important to note that aliases also occur when you pass in a list as an argument. So once you create a parameter, that parameter has a copy of the address, which is an alias to whatever argument we passed in. So let's use all that information to solve the next programming task, which says write a function that accepts a list as an argument and returns a unique copy of that list. Unique copy here meaning a non-aliased copy. So we have all the same values as our original list, but we're not pointing to the same address. So for example, if I have a list x, which is just a list 1, 2, 3, 4, and we call this function on it, the result would be equivalent, so x would equal the result, but it wouldn't be the same list. So equality comparison would be true, but identity comparison, x is y, would be false. So the idea behind this function is we want to prevent aliases. We can't just say x equals y, we want to have some sort of function that we can give our list to that function and get back a unique copy of that list. So in terms of a design, what we're going to do is make a new list in memory and then copy all of the individual elements from our original list one by one. Because those elements are primitive types, or so we'll assume, we don't have to worry about mutability, so we don't have to worry about aliases when we copy them. Okay, returning to our previous code, let's clean up our last example here. Comment that out for later. And there's our big function, so let's just put it here. We'll make a new function, we'll call this def copy list. And that takes in some list. I'll just call it lis for short. Now, the idea is we need to make a new list in memory. So at some point, we're going to have to create a new list. So let's initialize some result list. We'll call it the copy list. And that'll just start off as the empty list. Then, in order to copy our inputs without copying the list itself, we need to traverse that input list so we can grab each individual element. So we'll say for x in our original list. For each one of those, we'll just take that value and copy it into our new list. So we'll say copy.append x. So because this variable is already a copy of the values in this list, what we have to do is just append the value to our result list. And then once we're done, all we have to do is return copy. Real easy. We're just traversing the list, appending into a brand new copy. But let's see how this works. So down at the bottom here, we'll run our code. We can use our original lists as inputs. So we'll just say my copy equals copy list, and then I'll pass in the nums list. Now, if this worked, my copy equals nums should be true, and my copy is nums should be false. So we could put these in if statements, but in this case, we're actually just concerned about those values. We could put asserts as well. I'm just going to say is not. So now these should be true. I'm going to say is not to create the negation of the is operator. If is was true, then is not should be false, and vice versa. So let's save and run our code. And we get two trues. So they have the same value, but they are not the same list. So copy list in this case, we went through and traversed our original list, copying each individual element into a new list. That's why the identity doesn't show up as true, but because we're copying all the specific values, then the equality does show up as true. Now it should be emphasized that this will only work if our elements are primitive values. And we haven't looked at lists of other lists, but this is what's known as a shallow copy, and it doesn't work if we have deeply nested lists. So it's a bigger issue than we can solve just yet, but we haven't even seen the problem, as we haven't seen nested lists yet. So we'll return to this topic later when we discuss deep copies later in this chapter. One other thing I'd like to point out is that in order to do shallow copies in Python, there are some shorthands, and I'll just type these into comments here. Say shorthand shallow copies in Python, whereas this is more of a long form shallow copy. To do shorthand shallow copies, if we could say something like list2 equals list1, and then just take a slice from the beginning to the end of that list, that creates a new list to house the slice, because remember, a slice doesn't modify the original list. It creates a copy of that list, and if we're starting from the beginning and ending at the end, then we're copying all the elements. So it makes a new list with all the elements copied. So this creates another shallow copy. Another way we can do this is by using the concatenation operator. So I could say list2 equals, and then the empty list concatenated with list1. This one seems less obvious that it would do a whole shallow copy, just reading through it. But the way this works is an empty list has no elements in it, so when we concatenate it to any other list, we end up with that original list. But the concatenation operation itself, because it has to end up with a new list, ends up creating a new list to house those values. So even though we're concatenating 0 elements onto our old list, it makes a new list to hold both of those values, which just happens to be the original value. So now returning to our merge list problem. This code worked, but we saw that it was destroying our input lists. So if I passed in X284 and Y619, it would merge the list and our result would be the thing that we were expecting, but then X was destroyed and Y was heavily modified. And this is happening because of aliasing. When we passed in the values X and Y, what we're passing in is the reference or the address to the lists that X and Y point to. So when we jump up to the top of our function here, we have list1 and list2. These are aliases to that same list. So when we mutated those lists by popping values out, we're mutating the original list as well. One simple solution, and there are a few solutions to this, but one simple solution to not destroy our inputs while we're doing this is to make a copy of our inputs and then destroy those copies while we work instead. So a really simple way to do this up front would be to say, start with our empty list, and then I'll just say make a shallow copy of our inputs to prevent modifications. So we'll say list1 equals list1 sliced. And list2 equals list2, and again, a full slice. So this takes all of the elements in list1 and puts them into a new list, which now gets stored back into the same variable. So elsewhere in memory, a new list was constructed, all of the items were copied over to that new list, and the address of that new list was now stored back where we were originally pointing to. So it's copying all the elements into a new list, but it happens to have the same variable name. Now when we save and run our code, let's test this merge code. Don't need this anymore, but we do want this. So before when we did this, we ran it, we saw X and Y weren't what they started with, but if we save and run our code now, when we're done, X and Y are unmodified. So we pass in X and Y, we're still making those aliases, but now when we go to the top of our function here, when we do this shallow copy, we're now breaking those aliases. And one last note that I want to point out, I'll just put this in the interactive mode again. One last thing about references when dealing with lists is when you're using append, that's going to mutate the original list. Concatenate will create a new list. So if I have some list X equals A, B, C, D, and I say Y equals X, so I make an alias between those two, so Y has the same value. If I say X dot append the letter E, X now has the letter E, and so does Y, because we have an alias between those two. Right? If I said X is Y, that's true. Now, if I were to say X equals X plus, and then the list literal that contains a single string F, but we're using concatenation, X is changed in a very similar way as if we had just appended it. But now if I ask if X is Y, that's false. So notice Y hasn't changed. So what's happening here is the shared list X is referenced at the beginning of this statement, and then we concatenate to that a new list F. And now the result of this concatenation is a brand new list that contains all of the original values. So up until this point, x is still pointing at its original list. Then we say x equals this new list. So x now points at this new list, and y does not. So you might be tempted to consider append and concatenate as very similar, but there is an important difference, and now you see it. Append actually goes into the original list and changes it, whereas concatenate creates a brand new list and just stores that instead. Okay, and that's it for references and aliases for now, at least. If any part of this was unclear, please make sure you reach out and get the help. We'll return to these topics throughout the rest of this course, and surely throughout the rest of your programming career, you will face these concepts as well. A misunderstanding of reference types leads to a lot of difficult to debug problems, so it's a good idea to understand it now when it's at its base stage before we get into more complex things like lists that contain other lists, or even more complex data structures than that. That's it for this video. Now on to the next one.